Hello, honors physics students. We're going to start here in our problem set with problem number 2, so go ahead and read this, try it, come back to the video. Okay, so it's nothing fancy here. We're definitely doing Coulomb's law, since we're trying the force between 2 point charges. If electrons are really, really tiny, you consider them to be just points in space. Of course, we're using Fe equals K, Q over R squared. The big Q and little q, it doesn't matter who's who in this case. Soon that'll matter, but right now just put one in one or the other. And of course, absolute value here, so even though the electron charges are negative, we're disregarding the signs on the charge, which will cancel anyway, even if you put them in, but it doesn't matter. Okay, now here's where we come to a bit of an issue. Notice that the answer is given in two ways here. The right number of sig figs and the wrong number of sig figs. And the reason I point this out is not only because we should always be practicing sig figs, but sometimes if you have a calculator that has a single line display, it may look like the answer on the right there. So for example, if your calculator looks something like this, it may look like this is 1 times 10 negative 8 if you count all these decimal places, and you may be tempted to say, well, it's just 1 or possibly 1.00. The problem is on these single line displays, what's actually happening is it's cutting it off because it doesn't have the room to show you what the next digits are. So in this case, you need to do something to get the right number of sig figs, and also to tell. You can't just assume it's going to be 1.00 afterwards. So one way to do this is you divide by the power of 10. If your calculator looks like this, you divide by 10 to negative 8, and then your calculator will show the remaining digits. Also, there may be some way to do it where you shift the mode. For example, this might be some sort of fixed number of decimal places, it might be a floating number of decimal places. Anyway, you want to do something that will show what the next digits are, in which case you can see here it's really 1.02 times 10 to the negative 8th as the proper answer. Alright, we're going to go to problem number 8. Here again, pause the video, try it all on your own, come back to see some answers. So hopefully you notice, of course, letter A is a review problem. It's about gravitational force, and here's our equation for gravitational force. F sub g equals g mm over r squared, or it could be m1, m2. Again, as we did before, it doesn't matter which is capital M, which is lowercase m, but you have to make sure you're putting the proper numbers in the proper places. This is about mass. Now, first of all, where are you going to find the masses of the proton and electron? You don't have to memorize these things off the top of your head. We did it just last class. So if you look it up on the chart we've done on our notes pages, we know the mass of the electron is given here, the mass of the proton is given here, and every electron is identical to every electron in the universe, every proton is identical to every proton in the universe. These are going to be the masses of these objects no matter what. And as I just mentioned, you do not have to memorize these numbers. It certainly is true after using them a number of times. You may commit them to memory, but they'll always be provided to you in the constants table on a quiz or a test. Letter B now is electrostatic force. Of course, we're using Coulomb's law. Now we're using the charge. So make sure you're using the charge on these objects, which, if you forgot, you could always look up on the chart we did last class. Here are the charges on the electron and proton. It's just a matter of making sure you're putting the right numbers in the right places. This involves masses, this involves charges, and I get it that these numbers all kind of look alike. They're all in scientific notation, they're all really small numbers, and even if you compare these numbers here with these numbers here, they look an awful lot alike. So it would be very easy to get confused, and that's one of the traps students tend to fall into. So just make sure you're putting the right numbers in the right places, and everything here is in scientific notation, so really make sure you're using your EE button, your EXP button, as I trained you to do. Since pretty much almost the beginning of the year and we're doing scientific notation, is a good chance that if you're not doing that, you're going to get some things wrong. So here are the answers for force of gravity and electrostatic force. As always with problems in scientific notation, I'll give you the same advice, that if you're getting the number in front correct, but the X one incorrect, you're typing it in incorrectly. This is what I was just alluding to. There's a good chance you're not using your EE or EXP button, and so when you're grouping things together, things are going wrong. And that's why you have to use your EE or EXP button, because it groups things together and eliminates these issues. If instead you're getting the number in front wrong, and everything is wrong, well, there's a really good chance you're not squaring the distance. So we saw this problem, exact issue back when we did gravitational force the first time. Now we're seeing it again when we do electrostatic force. So just make sure when you type the number in the bottom, this is the distance between them, don't forget to hit that X squared button. An issue that for some reason some students have had since the beginning of the year. It's carrying over into the rest of the year, but you have to do it. As soon as you type in the distance there, you hit your X squared button, it'll square it for you, and then you're going to get the right answer. So if you're getting anything wrong, make sure you try it again until you can get these numbers correct. Okay, we're going to work on problem number 7 now, so go ahead and read this, try it on your own, then come back. Okay, so first of all, notice that yes, we're talking about two tiny objects here, which is a good indication we're going to be using Coulomb's law. Remember, there are restrictions on Coulomb's law. One of them is that it only works for point charges. There's got to be something in the problem to indicate that we're talking about tiny, tiny objects with net charge. Of course, to be Coulomb's law, we have to rearrange, and here we're solving for distance. And so, I've been training you for this since the beginning of the year. We always rearrange algebraically first. If you didn't do that, pause the video, practice the algebra, then come back. Alright, so here's Coulomb's law. Now we're solving for r, the distance between them. So just flip-flopping here, taking the square root. I definitely think you should be able to do this, with your algebraic skills. It should not be an issue whatsoever to solve for r. And we always do this because it's easier. It's always easier to manipulate numbers once rather than manipulate numbers twice. You really should not just be putting the numbers in here and then doing it, because there's a lot going on here. Also, I assume you noticed that the units here are not given in coulombs. We must do a conversion, although as I've shown you before back when we were doing the light topic, the best way to do this is just replace the metric prefix with this power of 10. Rather than moving decimal points around and doing unit conversions, this is the simplest way of doing it, and it really leads you to success. So this one here is nano, which should be fresh in your mind back when we were doing light. Remember, nano is 10 to the negative 9th. Nano, 9, even sounds like it. And this one here is mu, which stands for micro. That's 10 to the negative 6th. And so you put your numbers in. Here's k. Here's the first charge, 10 to the negative 9th. Here's the second charge, 10 to the negative 6th. And there's the distance. And so if you're getting a number like this with 7 and 0, 0, but your power of 10 was way off, there's a good chance you either had the wrong power of 10 or you just completely forgot to convert, which at this point in the year really should not be an issue. You have to be looking for those things. You can't miss that stuff. And of course, don't forget to take the square root at the end. All those issues come into play here. Let's take a look at problem number 10. Go ahead and read it, try it on your own, come back. Alright, so here are these classic problems here where we're taking the equation, we're manipulating some algebraic terms in it, we're pulling those terms to the outside and then seeing what happens. So for letter A, we should be getting a quarter Fe. It should make sense, right? If we have a smaller charge for each of these, we should have a smaller overall force, but just in case you need to see it spelled out for you, here's Coulomb's law, its original form, and then you replace one of the charges with half of it, the other charge with half of it, you take a half times a half as a quarter, you pull it to the outside, you'll see it's a quarter times the original, so it's a quarter Fe. Letter B should be 1/9 Fe, which should make sense because if the distance is tripled, you should expect that they exert less of a force on each other. And here is how this is worked out. We have kq1, q2, or kqq over 3r squared. Now, at this point, if you leave it like this, there's a good chance you're going to get it wrong. Hopefully, you recognize this just like other problems we've done, because this looks like you get 1/3, we should be getting 1/9. What do we need to do? You better be putting parentheses around it. I've been training you for this again since almost the beginning of the year. We put parentheses around whatever the term is so that when it's raised to the exponent, we know the term inside. The constant is also raised to the exponent, so that's going to be 3 squared. It's going to be 9 in the denominator. Pull it to the outside. That'll be 1/9. Very standard sort of solution. Letter C is going to be a very similar problem here. It's going to be 4 times the original force. Letter D is 3/4 times the original force. Letter E is 16/5 times the original force. If you need to see any of those in more detail, please email me and I'll lead you through a solution for that. But a lot of them are issues just like this, where again you want to make sure you put parentheses around anything with a distance so we know whatever factors inside is squared as well. Again, these are very classic sort of problems. You should expect to see these. We've seen these before. Very, very classic sort of problems.